Now we want to make a little warning here to watch the sign. Watch the sign of your axial force. So just to repeat what we just did, if we have the reaction force that's going this way, and then we've got the assumed tension force going like so, again, we solve this and we find that P1 is equal to -6 kips. Well, immediately that tells you, with the negative sign, that that bar is in compression. So as soon as you see a negative sign, you can think bar 1 is in compression. And if it's in compression, that means its length is shrinking. It's getting smaller. So as you look at the entire bar, and you look at that entire system, like so, what that tells you is this point, the end of bar 1 is moving to the left. It's getting shorter, so it moves left. Let's write that up. And it's difficult to assign a sign to the direction because it depends on where your support's going to be. In other words, if you had a bar over here and that was the fixed support and it was getting shorter, it would be moving to the right. So I think it's better at this stage to use your intuition and the arrow, the left or right arrows. So we want to use our intuition and either this way or this way. And this will take a little bit of practice, but what you're going to find is after a little while, it's going to become somewhat second nature. So now we're in a position then to find out the movement of point C. So again, this is B, C, and D. Now we already know that it's going to be to the left because we just determined that the bar is in compression. So for that segment, we would say delta at C. Now what that really is delta of C relative to B, because that's the fixed support. There is no displacement at that location. So in this case, we're saying how much does bar C move relative to the fixed support? And that's going to be the PL over AE, all in bar number 1. That's it. Bar number 2, other than transferring the initial load that impacted the reaction, it has no influence on this displacement. So we can rewrite it. We would say P1 L1 over A1 E1. So those are the numerical values that we would get. Now at this point it's okay, I think, to leave off the sign on P1. We know that it's negative, but you've already made the interpretation that's going to be to the left. So if you want to, I think it's fine to say that's going to be 6 kips, that's the force, times the length. It was 1 foot, but remember, as soon as we have used the KSI or PSI, that means everything has to be in inches. So a common mistake is to forget that. So it's 12 inches. So let's say watch the units on your length. Then the area, again, that's 2 square inches. And then the value of E is 20,000 KSI. So again, that K is matching that K. So we've got the load in kips, and then we also have the value of E in kips. So those are going to cancel out. So be careful that all your units are consistent. If you had this in PSI, then it would be 20 million PSI. Then you would want to convert the numerator to 6,000 pounds. So be careful about that. By the way, remember that K, when we write it like that, that's kind of a combination. That means kilo pounds. It's a ad hoc designation. It means 1,000 pounds. So we do that, we crank it on through, and it's 1.8 times 10 to the -3 inches. And again, the bar is compressing, so C is going to be moving to the left. So let's rewrite that up for whoever has asked us to solve this problem. Delta C is going to be equal to 1.8 times 10 to the -3 inches moving to the left. So we're not going to say minus or plus on these displacements. We want to use physical direction, because the very first question that someone's going to ask us is, what does your sign convention mean? What is plus? What is minus? This way, if you say it's moving to the left, it is crystal clear. Now, what about point D? Point D is a little bit more complicated because notice what's happening. Let me redraw our system once again, like so. Not to scale, obviously. This bar is shrinking, so this point has moved to the left. This bar, on the other hand, notice it's got the 4 kip load going like so. Well, we don't even have to do the statics calculation on this to know that that bar is going to be in tension. If we make the cut, draw an assumed tensile force, we know that the second bar, bar 2, is going to be in tension. So it is growing in length. So what that means is that D is moving to the right of C relative to C. So that bar is going to be stretching. So what you have to be careful of, again, is your sign convention. So again, watch out for the statics. So we need to get statics for getting P2. And you can use, again, either the left-hand side or the right-hand side for your free body diagram. Let's do both to make sure it gives us the same thing. So there would be the bar 1, and then we could chop off any segment of that one. We have 6 to the right. We have 10 to the left. That means our assumed tensile force is going to be 4 kips if we do the statics calculation. So that would be this free body diagram. I could also do the right free body diagram. There's the right side of bar 2. There's the 4 kips. And then there's our assumed bar force, P2. And we see that that's going to be 4 kips. So P2 is equal to plus 4 kips. That means it is in tension, and that means that the bar is growing longer. So again, D is moving to the right of point C. So now what we would have to do is the following. We would say that the delta of point D relative to B. So again, earlier we had C relative to B, but now we've got D relative to B. So that's going to be the delta of C relative to B plus the delta of D relative to C. Now, a lot of times you'll see people shorthand this. They'll say, well, this is just going to be delta C, this would just be delta D. And it's kind of implied that you're measuring it in reference to something else. But a lot of times it's nice to put these relative motion symbols in there that most of you have seen or will see from dynamics. So remember, the first part we already did. That's 1.8 times 10 to the minus third inches to the left. Plus, then, we're going to have the movement of D relative to C. Remember, that's stretching. So that would be, the bar is going to be growing. So that means D, no matter what we have as a number, that's going to be going to the right. So that would be our PL over AE. So that's going to be 4 times 2 feet, that's 24 inches, all divided by its area, and that's going to be 1 square inch times its value of E, which is 10,000 KSI. So those values, and by the way, when we do this one, that turns out to be 9.6 times 10 to the minus third to the right. So clearly the one to the right is dominating. We're getting more stretch that way. So we have this value to the right, and then we're subtracting that value since it's going to the left. So our final displacement of D, or parenthetically you could say it's really delta of D relative to the fixed support, but almost always we are always measuring it in terms of some absolute motion to a fixed point in space. And that's going to turn out to be equal to 7.8 times 10 to the minus third inches to the right. And that would be our final form that we would box up like so. That's our first application then of a deflection for an axially loaded bar. And it is one then that has a lot of uses for us. Even a problem as simple as you're sitting in a chair, we could calculate what the deflection would be for cases like that. If we've got hanging a chandelier from a wire, we could figure out how much axial displacement there's going to be from that particular displacement and so on. So this is a very common problem, formula, approach. Let's go ahead and say it is a very common problem. We could probably look around whatever room we're sitting in right now, and we can see a number of systems that are going to be then loaded by some sort of axial force, and we can calculate that particular value. Now, there is another class of problem, and that is the axial displacement when we have P, A, and E that are going to be non-uniform and non-uniform within some segment. Here, for the example problem that we used, we could apply PL over AE piecewise. But what happens? What happens when either P, A, or E varies with X? Question mark. We're probably then going to have to integrate. Now, this would be a natural time for us to be able to do this, but what we're going to do is we are going to wait on this topic. And the reason we're going to wait is we want to get through our next subject. It's really kind of our biggest topic so far in the class, so that we can have all of our material done in the time for exam number 1 for this class. So we're going to wait on this as a matter of timing and bring it back then after we finished our next topic. So it's strictly for timing. It is a good time to do it right now, but again, what we want to do is race our way through and understand axial bars a little bit better to introduce our next topic. So we'll say then we'll bring this back after our next big topic. And what is our next big topic? Well, I'm looking at the timer and we're just at about 12.5 minutes. So you're going to have to wait for the last part of today's lecture, because for now we're done with part 3.